So we've just seen that the acceleration of a material element is probably one of the most important concepts that we're going to have to use. And we've written this in terms of our idea of a material derivative, which is the total derivative associated with changes in velocity. And that can be coming from both position constant and time rate of change, as well as changes associated with changes in position. And you can see some examples of that in the video that we've mentioned. So it's always important to be able to write out what a mathematical variable such as this means. And so it's worth us just saying in words what we really mean. This side is what we might call the acceleration following a material point. Which we've written as x. And that's what we mean by this material derivative in an Eulerian sense, and this would be the equivalence statement in a Lagrangian way. So this is an equality between it. The way we evaluate this quantity, which is a Lagrangian quantity in terms of Eulerian variables, is what we've written out on this side. And so we might think about this as the time rate of change, in this case of the velocity, at a fixed point. So that's that quantity. But then there's another quantity as well, which is this term that we've called the advective acceleration, associated with changes in position. And so these two added together is what we mean by the total acceleration. And this operator can be quite confusing and quite difficult to evaluate. And so it's worth us thinking a little bit about how we might evaluate this term. So we're interested in this advective operator, which is v dot grad v. If we were to try and make it a little simpler to understand, we might think about it as the dot product of a velocity and the gradient operator. And then that quantity, which is a scalar, is going to operate on this vector quantity v. And so we can then think about trying to evaluate that. And so we'll do that by thinking about this in terms of its individual components. So maybe we'll write this out for a component, say the acceleration ai, which is the time rate of change following a material element of a component vi. And so we'll have to take this quantity, dvi by dt, at a fixed position in space. And then we're going to have to take this operator and we're going to have to evaluate that. And because these are vector quantities, we really need to give each single component its own base vector. So we'll write the velocity this way. That's being multiplied by the gradient operator, d by dxj, and that's going to have a base vector associated with it. And then once we've evaluated that, what's going to go into the operator here is going to be the component vi. And so this will go into here. And since we see repeated indices here, we should really recognize that this is a double sum over both j and k. And so we're going to have to do that summation to evaluate this. So just as a reminder, if we think about our base vectors being 1, 2, and 3, we would write these in terms of E3, E2, and E1. And when we take a dot product of EJ and EK, unless they're in the same direction, then they're considered normal. Then we would say that EI dotted into EJ is going to be expressed in terms of the Kronecker delta, which is equal to 1. So delta ij is equal to 1 if I is equal to j, and delta ij is equal to 0 if I is not equal to j. So in this case, this is a standard identity. Here we see that the summation is over j's and k's. So if we take the dot product of ej and ek using this kind of identity, we would say that this would be equal to delta jk. And then that will only be 1 if j and k are equal to each other. And so j and k are equal to each other, which is what we've got here. And so we'll have to write this as vj d by dxj of vi. And that will be summed now over j. So we'll have dvi by dt, constant x, plus this, and that whole quantity is our component of our acceleration here. So it's worth at least once writing this out, and so as an exercise, it would be good for you to write this out, and because we'll have terms that will look like v1 d by dx1 plus v2 d by dx2 plus v3 d by dx3. And in each case, we'll have a quantity that will go in here and here and here. So when you write this out for all 3 components of velocity, you'll find that you get 3 by 3 or 9 components that you'll have to evaluate. And we're going to do next an example where we'll actually try and use this idea of a material acceleration.